we talked about crystal symmetries, and we saw that a crystal is invariant under a translation of the form n1a, n2b plus n3c. So this n1, n2, and n3 were integers, a, b, c were basis vectors. So it's basically the lattice is invariant under translations, or there is translational invariance. There are several ways to say this. Okay, so what does that mean in terms of physical properties of the crystal? Well, the electron concentration, magnetic moment, etc., these are also periodic within the crystal, and they are invariant under a lattice translation. So if you go from one lattice point to another lattice point using this lattice translation vector, we will find the same electron concentration, same magnetic moment, etc. So the electron number density, n of r, is a periodic function of the position vector r with periods a, b, and c. So if I look at the electron concentration at one point at r, lowercase r, position vector, and if I have a displacement in the amount of capital R, a lattice translation vector, I will find the same electron concentration. Now, with these observations, I want to go back to an important theorem, that's Fourier's theorem. So if you have a periodic function, let's for simplicity start with one-dimensional case, n of x, where n of x plus a is equal to n of x. So we have a periodic function, the period is equal to a. This can be expanded into a Fourier series. We can write it as a sum of cosines and sines. So n of x can be written as n0 plus sum over p equals 1 to infinity, p is an integer, Fourier coefficients cp cosine 2 pi xp over a plus sum from p equals 1 to infinity sp, so I have chosen c and s to denote cosine and sine, sine 2 pi xp over a. So I have a sum of cosines and sines representing my function n of x. So these cp and sp are real constants, so they're called the Fourier coefficients. Okay. Now, let's verify this. If I look at n of x plus a, it would be n0 plus sum from p equals 1 to infinity cp cosine 2 pi px. Instead of x, I have x plus a divided by a, plus sum from p equals 1 to infinity sp sine 2 pi px plus a over a. Now, let's remember an important property of cosine and sine. Cosine a plus b is cosine a cosine b minus sine a sine b, and sine a plus b is sine a cosine b plus cosine a sine b. So if I use this for cosine 2 pi p x plus a over a, I will have first cosine 2 pi p x over a, cosine 2 pi p a over a, and then minus sine 2 pi p x over a, sine 2 pi p a over a. Now sine 2 pi p, because p is an integer, is 0, and cosine 2 pi p, because p is an integer, is 1. So it's like cosine 0, cosine 2 pi, etc. So I find that the second term is going to disappear. The first term gives me just cosine 2 pi p x over a. And as for the sine term, sine 2 pi p x plus a over a, I have sine cosine, sine 2 pi p x over a, cosine 2 pi p a over a, plus cosine sine, cosine 2 pi p x over a, sine 2 pi p a over a. Again, the a's cancel. Sine 2 pi p, sine 0, sine 2 pi, sine 4 pi, etc. is 0. Cosine 2 pi p is again 1. So I find sine 2 pi p x over a. So what do I conclude? N of x plus a is equal to n of x. So indeed, if n is a periodic function with a period a, it can be written of this form, the Fourier theorem, n0 plus a sum over p equals 1 to infinity, a coefficient times the cosine and a coefficient times the sine 2 pi p xp over a. Okay, so we have shown this. Now the term that ensures the periodicity here is 2 pi p over a, and we say that 2 pi p over a is a point of the reciprocal lattice. So why is this 2 pi p over a? Well, so you can notice that 2 pi times p an integer, and I have a number divided by a. A is my periodicity of the lattice, so it could be the lattice constant, for example. And then I would have the dimension 1 over length. So L is length here. So this is 1 over length. So therefore I see that this is a reciprocal lattice. And in one dimension, these points will fall on a line with spacing 2 pi over a. So it will be 2 pi over a, 4 pi over a, etc. P equals 1, p equals 2, etc. And we can also write this Fourier series in the form, instead of using sines and cosines, using Euler's theorem. It can be written as an infinite sum from minus infinity to plus infinity over the integers p. The modified coefficients now np e to the I 2 pi p x over a. And remember that e to the I theta is cosine theta plus I sine theta. This is Euler's formula. So we can use this because it's also a sum of cosines and sines. It can be written in this form. And if you generalize it to 3 dimensions, it can be written as a sum over a set of vectors g n sub g e to the I g dot r. So it's a dot product between a vector g and a direct lattice vector r. So for this to satisfy the Fourier's condition n of r plus capital R, so if I go from the lattice point r to r plus capital R, I should have n of r is equal to n of r plus capital R. So looking at this, if I substitute e to the I g dot r plus capital R, I see that e to the I g dot r should be equal to e to the I g dot r plus capital R. So that means e to the I g dot capital R must be equal to 1. So that's basically what determines the vector g here. And this function n of x has to be a real function. So this is basically ensured by noting that the coefficients that we choose here for the one-dimensional case, these coefficients n p should be satisfying the following relationship: n sub p is equal to n sub minus p complex conjugate. So these coefficients, because the Euler's formula gives me a complex number, these coefficients should be rather complex numbers in order to get a real function n of x here. So we will see that these coefficients should satisfy np equals n minus p complex conjugate. Okay, so to show this, let's call 2 pi p x over a phi. Then we can rewrite this n of x as some p greater or equal to 0 np e to the I phi plus n minus p e to the minus I phi. So I have basically separated this into e to the I phi and e to the minus I phi terms, and that takes care of minus infinity to 0 and 0 to infinity. So if it's just a summation p greater or equal to 0 to infinity, basically this is the same thing as the summation from minus infinity to plus infinity np e to the I phi. Okay, so this is basically using Euler's expansion now, np cosine phi plus I sine phi plus n minus p cosine phi minus I sine phi. So if I take this into cosine phi parentheses, cosine phi, I have a term np here and then a term n minus p here. So cosine phi np plus n minus p, and I sine phi np and I sine phi minus n minus p here. So if I group them together, this is what I get. And then I note that if np is a complex number, it has a real part of np, plus I times imaginary part of np. And for n minus p, I have a real part of n minus p plus I times imaginary part of n minus p. And what is complex conjugate? That's by definition real part of n minus p minus I imaginary part of n minus p. So this condition, I said np equals to n minus p complex conjugate must be satisfied. Well, that will imply the real parts should be the same, imaginary parts should be opposite, with the opposite sign. Okay, so if I write n of x sum over p greater or equal to 0, cosine phi parentheses, for np plus n minus p, I substitute real part of np plus I imaginary part of np plus real part of n minus p plus I imaginary part of n minus p. And since I noted real part of np is equal to real part of n minus p, I will replace the real part of n minus p with the one in red, real part of np. And for imaginary part of np, I will replace with minus n minus p. I will replace it minus I imaginary part of np. Okay, and for the sine term, so that's this one, cosine phi minus I sine, no, np minus n minus p in I sine phi parentheses. So that gives me real part of np plus I imaginary part of np minus n minus p, so minus real part of n minus p and minus I imaginary part of n minus p. So minus real part of n minus p is also minus real part of np. Minus I imaginary part of np is also plus I imaginary part of np, because I have np is equal to n minus p complex conjugate. Well, if that's the case, so when I substitute these two, I will see that for the cosine term, I will have two real parts of np. So these two will be added together. However, these two would cancel. And for the sine part, the real parts would cancel. And the imaginary parts would add up to give me 2I imaginary parts of np. But because I have an I here, I times I remember is equal to square root minus 1 here. That's the imaginary number, square root minus 1. So I obtain I squared, that gives me a minus 1. So at the end, I find that n of x is sum over p greater or equal to 0, 2 real part of np cosine phi minus 2 imaginary part of np sine phi. So this is indeed a real function. So therefore, if this condition is satisfied, the coefficients, complex coefficients np are equal to n minus p complex conjugate, n of x becomes a real function. Okay, how do we calculate these Fourier coefficients n sub p? It's calculated using this inverse Fourier transform, 1 over the period, integral over 1 period of the periodic function e to the minus I 2 pi p x divided by the period dx for the one-dimensional case. So this would give me for the coefficients np 1 over period is a, integral over 1 period 0 to a, n of x e to the minus I 2 pi p x over a dx. Now let's show that. So we are suggesting that np is equal to 1 over a integral dx n of x. For n of x, I can substitute sum over p prime np prime e to the I 2 pi p prime x over a. So that's, if you go back here, that's n of x. Sum over p np e to the I 2 pi p x over a. Because I already have p here, I change it to p prime in the integral. So this becomes sum over p prime. From minus infinity to plus infinity, np prime e to the I 2 pi p prime x over a. And then I have in the Fourier transform minus e to the minus I 2 pi p x over a. Now it doesn't matter if I do the integral first or the summation, so I take the summation out, sum over p prime and p prime, and then I have the integral from 0 to a dx e to the I 2 pi, and as you can see I have p prime x and minus px, so they will add up e to the I 2 pi p prime minus px over a, and that gives me 1 over a sum over p prime and p prime. I perform the integral. The integral gives me a over I 2 pi p prime minus p e to the I 2 pi p prime minus px over a, integrated from 0 to a. So if I substitute a here, I will have e to the I 2 pi p prime minus p. If I substitute 0 here, I will have e to the I 0. P prime minus p is an integer, so it will be e to the I 2 pi an integer, which is 1. So it will be cosine 2 pi integer plus I sine 2 pi integer. It will be 1. And minus e to the I 0 is also 1, so that will give me 0. So if p prime is not equal to p, I will obtain a 0 from this integral. On the other hand, if p prime is equal to p, if I look at my integral, I will have 1 over a sum over p prime and p prime. Now I have performed the summation and I'm only left with the p term, so it is np. And then I have integral from 0 to a dx e to the I 2 pi p prime is equal to p, so p minus p, which is 0, so that's 1. So I obtain 1 over a and p integral 0 to a dx, 1 over a and p, a's cancel, and I find np indeed. So this integral gives me a non-zero value only for p prime equals to p. So indeed I find that these coefficients are calculated using the inverse Fourier transform of this form. Now, in 3 dimensions, if I generalize this, the period in 1 dimension A is replaced by the volume of the unit cell. So it's 1 over the volume of the unit cell, integral over the unit cell volume dv, n of r. It was written as ng e to the ig dot r, remember? So in the inverse Fourier transform, I have the integral n of r integral multiplied with e to the minus ig dot r integrated over the volume. So 2 pi p over a is replaced by the reciprocal lattice vector g, and vc is the unit cell volume. Now this reciprocal lattice vector can be generated using the following. The reciprocal lattice vector A is 2 pi b cross c divided by a dot b cross c. What is a dot b cross c? That's the volume of the parallel pipes created by the primitive translation vectors a, b, and c. So that's the volume of the unit cell. And b vector is 2 pi c cross a dot b cross c, and c vector is 2 pi a cross b divided by a dot b cross c. So what is happening here? For a vector, I have used b cross c. So this was used to generate a vector. And for the b vector, I have used c cross a, and for the c vector I have used a cross b. So this is a cyclic permutation, so you can see that that's what I'm following. So 2 pi cross product of two primitive lattice translation vectors divided by volume of the unit cell gives me the reciprocal lattice vectors. Now why 2 pi? This 2 pi factor is included to make the reciprocal lattice numerically as well as dimensionally. This is the same as the wave vector k. So k is 2 pi over lambda. So basically we are going from direct space to k space. So we have this translation, direct space to k space, where we have the reciprocal lattice. Now you can see that if A, B, and C form an orthogonal set, for example, if we have a cubic crystal, then B cross C will give me A. So that's the cross product. B cross C gives me A cross B gives me C, C cross A gives me B, etc. So I find that A vector, capital A vector, should be parallel to my primitive lattice translation vector A, B vector should be parallel to B vector, etc. And the dot product, A dot product with A, the direct lattice vector A gives me 2 pi For the B vector, I get 2 pi. For the C vector's dot product, I get 2 pi. However, if I take the dot product of capital A vector with the B vector, I get 0, etc. So basically, capital A, capital B, and capital C vectors also form an orthogonal set. So the points in the reciprocal lattice vector are mapped by using the G vectors of the form HA plus KB plus LC, which we show as G sub HKL. So let's show that this is really working. So n of r plus capital R must be equal to n of r. So n of r plus capital R is sum over g and g e to the I g dot r plus capital R. So that means e to the I g dot capital R must be equal to 1. So what is e to the I g dot capital R? It is e to the I HA plus KB plus LC dot product with MA plus NB plus SC. So these are all integers. So dot product of A with capital A with A gives me 2 pi. So 2 pi HM, then I will have 2 pi KN, 2 pi LS, which will be e to the I 2 pi an integer. So that's equal to 1. So indeed, GHKL is a reciprocal lattice vector. So this is working when I have the dot product of A, capital A with the lowercase a giving me this 2 pi factor. Okay, so GHKL is a reciprocal lattice vector. So all reciprocal lattice vectors can be written in this form: HA plus KB plus LC, the capital letters ABC, where ABC are generated using direct lattice translation vectors, primitive vectors, lowercase ABC with this transformation. So there's a final remark here. The microscopic image, if you look at the lattice under the microscope, you get the real direct lattice imaged. But as we shall see, when we use diffraction pattern, when we look at the wave diffraction, the K-space is what we are going to image. So that's the reciprocal lattice. And the vectors of direct and reciprocal lattice are related to each other with the following properties. The GHKL reciprocal lattice vector is actually normal to the HKL plane of the direct lattice. And therefore the distance between two parallel HKL planes will be given by 2 pi magnitude of the reciprocal lattice vector GHKL. Okay, so in summary, we talked about the reciprocal lattice. If we go from the direct lattice, where we have translational invariance with the lattice translation vectors n1a plus n2b plus n3c, we see that when we go to the reciprocal lattice, we have the reciprocal lattice vector G, which is HA plus KB plus LC, and we can go from the direct lattice to the reciprocal lattice using this transformation, and this is just a result of the Fourier Theorem. Basically, since the direct lattice in 3 dimensions is a periodic pattern, it has to satisfy Fourier's Theorem. So the Fourier coefficients are obtained by the inverse Fourier transform 1 over the period integral over 1 period the dv n of r e to the minus ig dot r, and in the specific case of 1 dimensions, we have these reciprocal lattice points that are separated by 2 pi over a. So we have seen some properties of this Fourier transform. Basically, we have seen that the 1-dimensional version, we can write the n of x, a real function, as a sum of cosines and sines. And we have seen that when we generalize it to 3 dimensions, we can write this as n of g e to the I g dot r, but now these coefficients and g are complex coefficients, and for the 1-dimensional version we have shown explicitly that these complex coefficients should satisfy np equals n minus p complex conjugate, and these coefficients are obtained using the inverse Fourier transform. And we had some final remarks about this. The reciprocal lattice vector, which can be written in the form HA plus KB plus LC, where A, B, and C are now the reciprocal lattice primitive translation vectors. The microscopic image gives us an image of the direct lattice. The diffraction pattern gives us an image of the reciprocal lattice. The reciprocal lattice vector GHKL is normal to the HKL plane, and therefore the distance between two parallel HKL planes is 2 pi divided by magnitude of